Okay, this is Lab 13, which is code converters. And what we're going to be looking at here is we're going to be looking at a 74LS47, which is a BCD to 7 segment decoder. We're going to be using a 74LS147, which is a decimal to BCD encoder. We're also going to be looking at a 7442, 74LS42, and we'll talk about that in a minute. We're not going to need the NAND gates, we're not going to need the AND gates, we're not going to need the 3-input AND gates or the hex inverter. We're going to be using a 7-segment display. It don't specify here, but we're going to have to use a common anode 7-segment display. And I'm going to introduce y'all to resistor packs, but we don't need the 220 and 1K, but we do need the 330. But notice here it says we need 10 of them. We'll explain that. So first of all, we need to make sure we understand the difference between an encoder and a decoder. So a decoder is a digital combinational logic digital circuit that takes a binary number and converts it into another numbering system or code. An encoder takes a code or another numbering system beside binary and converts it into binary. So the 74147 is an encoder. The 74LS47 is a decoder. And also the 7442 is a decoder. So we'll be looking at that. So of course you also need to read the discussion on the lab. So right now you probably need to pause it and read the information section. Anything inside this section can be on a test. First of all, it says examine the data in the BCT, the decimal truth table in this figure. From the truth table, it's asking us to design a circuit to implement the decoding logic. We're not going to do this because this would be a very complicated circuit, and I don't know why they want to do this. What we're going to do is we're going to go ahead and use a combinational logic BCD to decimal decoder called a 7442. What you need to do now is go ahead and pause the lecture and then go into Blackboard into data sheets and look up the data sheet for a 74LS42. Once we look at the data sheet, we'll notice that it says it's a decimal decoder. Some people call it a 4 to 10 decoder. Some people call it a decimal to BCD decoder. But it doesn't actually give us BCD. What it's going to do is it's going to give us a decimal number, an indication of what binary input we put on the thing, which would be BCD. So we can actually put in, and by the way, this is one thing I needed to bring up, is that when you're looking at a integrated circuit, you start seeing this, A, B, C, D. The first thing I want you to think about is weighted binary numbers, with A being the least significant binary bit, and then B would be the to the second, to the third. I'm sorry, to the 0, to the second, to the third, to the 0, to the first, to the second, and 2 to the third. So what I'm going to do is I'm going to come over here and I'm going to put a binary number on the inputs, and this guy's going to come up here and decode that for me and cause one output to go low. Notice the outputs are low active. So if we look at the truth table, if I put all O's on ABC, now notice they have it laid out in weighted binary with A on the right and D on the left. So right here, this would be a binary 0. Okay. And of course, notice the output 0 goes low. This would be a binary 1. And then output 1 goes low. This would be a binary 2, so output 2 goes low. This would be a binary 3, so output 3 goes low. This would be a binary 4. So output 4 goes low. This would be a binary 5. Can't do this. This would be a binary 5. So output 5 goes low. This would be a binary 6. So output 6 goes low. This would be a binary 7. So output 7 goes low. This would be a binary 8. So output 8 goes low. This would be a binary 9. And output 9 goes low. Now over here, they're calling all these invalid. Now, technically, they're not really invalid. It's just that there is no output pin for output, because this is giving us a decimal number that represents a BCD input. And BCD goes from 0 through 9. There's no such thing as a single 4-bit number that would be 10. So what the 7442 does, it does not blow up if you put something above a 9 on it. What it does is all the outputs will go high. So you notice the pin out. So it's standard on this one. The VCC would be on pin 16 and our common would be on pin 8. And like I've told y'all, this is one of the most misused electrical terms in electronics. Is we use the term ground when it can be a ground, but it doesn't have to be. It could be a common. Here's my ABCD input. So these are my binary inputs, and these are my outputs. Now this is what gets people confused. Is now all of a sudden we have a pin out, which gives us what's assigned to each pin, and then we have a pin number that goes along with that. So this gets people confused every once in a while. Pin 1 actually has 2 numbers associated with it. It's got the pin number, and then it's got the signal's name. So pin 1 would be output 0, pin 2 would be output 1, pin 3 would be output 2, pin 4 would be output 3, pin 5 would be output 4, pin 6 would be output 5, pin 7 would be output 6. Pin 9 would be output 7, pin 10 would be output 8, and then pin 11 would be output 9. Okay. So what I've done is I've constructed the circuit. So what we're going to do, instead of designing the thing, which would be very complicated, we'll look at the data sheet here and see if they've got the actual circuit. So this is the circuits for a 74LS42. Now what I'm trying to get across, this is nice to know information. It's not required, it's nice to know. Because if the thing what we need to know is how the logic circuit responds to the inputs. We know we can put 16 inputs on this thing, 2 to the 4th. We know we can put 16 inputs on here, but only 0 through 9 will be decoded. Only binary numbers, only 0 through 9 would be decoded. After that, all the outputs would go high. So this is nice to know. So I don't know what the lab book was expecting us to do to design this thing. I could have designed it because I'm familiar with decoders, but it would be extremely hard for you to design that. So what we're going to do is we're just going to go ahead and do the rest of the lab on the 74LS42 or the 7442. I think mine's an LS version. Of course, now we know the difference. So the one without the center letters, these are what we call the standard series. These are the first TTL gates that actually come out. And then they came out with other versions that varies the speed and the power characteristics. So the LS series has comparable power characteristics. It has a lower power characteristics than a standard series, but it operates at the same speed. So now we got a chip that does basically the same as the standard series, but it consumes less power. And if it consumes less power, that means my power supplies can be smaller, which means my design can be cheaper. So what has happened when the LS series came out, it basically did away with the standard series. We can still get them and you'll still run into them, but basically the predominant logic in slower speed applications would be the LS series. And then we got the advanced low power Schottky, which is the ALS series, which is a really fast series. It's got a propagation delay of around 5 nanoseconds. We have the S series, which is the fastest TTL version we have out there, and it has a propagation delay of around 3 nanoseconds. So the LS series, I think, has a propagation delay of around 9 nanoseconds. That's on standard gauge. Now, the propagation delay for this is going to be more because this has to go through a lot of circuits to get to the final output. So this has a propagation delay. So this is my propagation delay of around a maximum of 30 nanoseconds, which is really good, and because it's an LS series. So what we need to do, standard TTL has a propagation delay of around 10 nanoseconds per gate. But remember, this has to go through multiple gates to get to the output. Okay, so this is what we're going to do when we come back to our lab. Is we need to draw the pin out. So it's a standard 16-pin dip, so you need to lay this out. And then what we need to do is we need to come back and assign these pins. Okay, so what you need to do is just go ahead and pause this and draw it as good as you can on page 94. We're not going to design our circuit. We're going to use the 74 LS or 7442. So when we look at the 7442, we see, and we've already looked at that, and I'm going to do mine in red, so we'll make sure we get that. So we know that this is DCC, and we know this is common, but of course the data sheet labels it as ground. But we need to know, and if them labeling it as ground is no problem, it's just that I require you to know the difference between a true ground and a true common. So pin 1 would be output 0, pin 2 would be output 1, pin 3 would be output 2, and then we can go right down the line. And then we come up on this side. And like I said, this gets people confused because they say, okay, output 8, and they want to hook it to pin 8, right? You understand that? And here's our inputs, A, B, C, and D. With A representing the least significant bit, and D representing the most significant bit. Okay. And then it's weighted binary we're going to put on that. Now we have 16 combinations, but remember this is a BCD to decimal decoder. So what's going to happen once we get above 9, which would be this, and this would be on the A, B, C, D inputs. Once I go up to 10, which the chip is not going to blow up, but all the outputs should go high. Now I've got this hooked up to the trainer. And notice on the truth table, the selected output goes low. Remember, our LEDs on our trainers come on when it sees a high. So this is going to be just opposite of what we see. So what's going to happen is when I put a 0 in here, all my LEDs are going to turn on. Now what I've done is since we do not have a 9 and a 10 on our, since we don't have an output 9 and 10, what I've done on 9, since all our LEDs go from 0 to 7 on the trainer. So what I've done is I've added 2 LEDs outside of this. And these are going to come on with lows, so these will operate just slightly different. So what I've done is I've taken this pin and I've put a light emitting diode right here. And of course the way the light emitting diode works, and we explained this in class, it drops around 2 volts, and we like to get about 10 milliamps through it, no more than 15 or 10. So if this goes low and I connect this to plus 5 volts, either it's going to blow the output of my 7442 or it's going to blow the LED. So what I have right here is I have a 330 ohm resistor, which is standard. Usually 470 or 330 are very popular for LEDs. And then I have the same circuit right here. So what this means is, but the only little difference, and then of course on this side I have this connected up to a VCC. And of course in digital, we need to know this. This will be on the next test. In digital, VCC is equal to plus 5 volts. VDD is equal to plus 12 volts. VSS would be equal to common, or they might call it ground, right? Okay, so I'm going to come over and switch back over to my camera. This is our pin out. So what I've done, as soon as I find my camera, so here's my circuit. Here's my 7442, and it is a 7432. It's not an LS, so it's a standard series. Here's my power rails coming down through here. So I've got my plus 5 running to this red wire. So these guys are common this way, and of course these guys are common this way. So what I've got, here's my switches. I'm using 0. I've got 0 hooked to pin. I got 0 hooked to pin 14, which is A. I've got my switch 1 hooked to my B input, which is, A is pin 15, I'm sorry. I got B hooked to pin 14. I've got, got 1 hooked to B, which is pin 14. I've got, switch 2 hooked to my C input, which is 13. And then I have switch 3 hooked to my D input, which is pin 12. So A, B, C, D. Okay. Now what we're going to see happen is these guys are hooked up so they come on when they see a low. These guys are hooked up, of course, internal circuitry, so they come on when they see a high. So right now what should happen when I turn it on is light 0 should turn off and all the rest of the lights come on, because right now I'm putting in a binary 0. Okay. So we notice that's a binary 0. So what we need to do is we need to set up a truth table. And the truth table you need to set up should look similar to the truth table that's on the data sheet. So the data sheet we've already looked at, it goes through, we have inputs that go from from 0 to 15, right? And then we need to indicate, so you need to leave yourself a pretty good deal of room, guys. You know that truth table is going to be pretty large. So what we got is we're going to set up a truth table, and we're going to do it very similar to the data sheets, which we're going to put A, B, C, D on our inputs. And then our outputs, we're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we're going to go through all our inputs from 0, 0, 0, 0, all the way down to 1, 1, 1, 1. And then we're going to come up here. So right now, what we have, now the light is off, so the light represents off, F represents a 0. So right now, this one's off, and all of these would be on. Now, what I'm going to do is mine's wired up backwards, so I'm going to put a 1 out there too. Okay. And then, of course, we're going to repeat this for all 16 possible inputs, 0 through F, right? So you need to go ahead and pause your lecture and go ahead and set up your truth table on your laptop. Okay, so first of all, we're going to start off by, so right now this is a 0, so this is a BCD 0, which would be 1 would be what? 0, 0, 0 on my switch. Okay. This is a BCD1, so notice the number 1 output went low, and then the number 0 output went back high. So I'm putting in a BCD1. Let me bring it up so you can see my switches. So we're not using these switches. These are the ones that we're using. I'm putting in a BCD1 and output what? Output 1 low. Okay, so record this in your truth table. If you need to pause the lecture, go ahead. Okay, so this is a BCD2, and notice output 2 went low. So what it's doing, it's taking a BCD input and giving me its actual decimal equivalent. But it can't do a decimal numbering system, so what it's doing is it's indicating it with the actual decimal digit with a light, right? In this situation, it turns it off. Okay, so I'm fixing to do a 3. So what we should expect is we should expect 2 to go back, light to come back on, LED to come back on, and then the 3 should go off. So there's a 3. Okay. And of course, this indicates a low, right? So the selected output goes low on the 7442. So the 7442 has low active outputs. So that's when you look at the symbol, it's got bubbles on all your outputs, or it's got bubbles on it. Okay, so this is going to be a 4. We should expect output 3 to turn off, right? Output 4, here's a binary 4, and output 4 goes to a low. Now these lights turn off with a low, so keep putting 0, 0. So this is 8 and this is 9. Okay, so there's 4. Here's 5. So output 4 light turned on, light put 5 turned off because it's putting a 5 and it's decoding a 5. Oops. Here's a 6. So output 6 went low. All the rest of them are highs. Here's a BCD 7. Output 7 went low, indicating I'm putting a 7 on the input. Okay. Now we're going to move down to these. These are going to turn on with a low, right? These turn off with a low. So here's an 8. So notice the 8 output went low. Because of the way that our LED is wired, it turns on for a low. Here's a 9. Okay, so output 9 went low. Turn this LED on. Okay, then we get, here's a 10. Notice all of them are high. These turns off with a high. Here's 11. Here's a 12. Here's a 13. Here's a 14. And here's a 15. So anything above a BCD, so these are all invalid BCD digits. That's why our BCD numbers that we can represent with 4 binary bits. Now we can represent any size BCD number we need, right? From 0 up to whatever, but each digit requires 4 bits. With those 4 bits, we can only legally represent numbers from 0 through 9. There is no such thing as a 1010 BCD, right? Y'all understand that? Some of y'all are still having problems on that. So probably on test 3, there is going to be number system conversions on test 3. Okay, so that's the 7442, which instead of us trying to design a BCD to decimal decoder, we used one that was already out there. So what we're going to look at now is we're going to look at a 74LS or 7447. So first of all, a 7447 takes a binary number, and automatically converts it over to a what's required to drive a 7-segment display. We're not going to hook this up because this is inside the trainer. But let's go back and discuss a 7-segment display. So this is a 7-segment display. And what we're going to do first of all is we're just going to see the segments. So what we're going to do now is we're going to do the pin out. So notice the spacing for the one that we're using is a standard 14 pin spacing, except this guy does not have a pin 4 and it does not have a pin 12. But it numbers it just like it was there. So this is pin 1, 2, 3. This would be pin 4, 5. I'm sorry, don't have a 5. 4, 5, 6, 7, 8, 9, 10, 11, 12 would be right there, 13, 14. Now why it did that? Because it uses the same spacing as a standard 14 pin deal. So what we're going to do is I'll go ahead and do this with you. What we'd do is we'd go to Blackboard and we'd look up the pin out. So the 7447 is a common anode driver, Okay, and it's a driver, which means it has the ability to output more than a standard chip would be, which would be around 16 milliamps for a standard, right? You understand series. This guy should be able to handle more than that, and we'll look at that in a minute. So what I'm going to do, instead of you going to Blackboard this time, what I'm going to do is I'm just going to bring up the data sheet. I don't know if I recorded this or not. I just noticed I had the lecture recorded. So on page 95, this is, pause. This is where we're going to do our pin out. It's asking for 2 pin outs. This says a 74LS 147 and a 74LS 147 and a 74LS 47. What I want you to do is I want you to do the 74LS 47 on the top because it is the first circuit that we're going to hook up, the 47, and then we'll come back and we'll do the pin out of the 74LS 147 later. So what you need to do is go ahead and turn to page 95 in your lab, and we're going to be working on the first one. So the 74LS or the 7447 is a 16 pin deal. In 7447, I went to Blackboard and looked this up. So first of all, what we need to do, let me bring up the 7-segment display first so we can understand what this thing does. So a 7-segment display, and it's given the name because it has 1, 2, 3, 4, 5, 6, 7 that we use to represent numbers and some letters of the alphabet, by the way. But 7447 doesn't do letters of the alphabet. All it does is numbers. And then it's got some weird outputs, and we'll come back and look at this in a minute when we look at the truth table. So we have 2 versions, and these are LEDs, and since we know they're 7-segment LEDs, this is not the correct symbol for an LED. It does not have the arrow pointing out. But if they had the 2 arrows pointing out, it would take up a lot of space, and you know it's a 7-segment LED. There's 2 versions of this. We can get this version right here, which is what we call a common cathode. So what it has, it's got all the cathodes inside the 7-segment display connected together, which means we're going to connect pin 4 and 12 toward common, 4 or 12. You don't have to do both of them. They just bring it out both sides of the 7-segment display so you can get the common to it most often. So what we're going to do is we're going to turn these things on with a high. Now what we have to understand is this is a diode. Once it turns on, it acts like a short circuit. So what that means is, guys, is we cannot come over here on these 7-segment displays. We cannot do this. We cannot turn this thing on by coming over here and putting. So this is the LED. I'm just going to draw one of them. So this is the true symbol for an LED. But we know it's a 7-segment LED display, so this would take up a lot of space because they don't use it. So to forward bias this thing, we have to put this toward the positive and we have to put this toward the negative. Now, common thinking is I can put this as to plus 5 volts and I can put this down to minus 5 volts or common, or minus 5 volts. Now, the problem is this thing turns on at approximately 2 volts. Anything above 2 volts is a short circuit. So what would happen is we would get as maximum current out of the power supply as we possibly can, and you would blow up the LED. Well, it wouldn't nearly blow up. I've seen them catch on fire before. We had a problem in DC is they look like light bulbs. They look like light bulbs. And so they got their trainer. What they'll do is they'll take these suckers in DC. We used to have LEDs in there. There was a lab on that. And they would take the LEDs and plug it right across the power supply and turn the power supply on and blow the LEDs or burn out the LEDs. So what we have to do is we got to come in here and we got to put in a resistor somewhere within this. Okay. So we can either come in and put a resistor right here and then connect this to plus 5 volts, or we could come up here and we could put the resistor right here. It's got to be in series somewhere, right, guys? And we can put this up. Then we can put this directly to common. Put the plus 5 volts there. So what we got is we got two options. So on this guy right here, this is a this is a common cathode. So I think they have them pointing. Oh, I'm gonna point them down. And I'm just going to do that. We know there's actually, there's either 7 LEDs in there, or there might be 8 or 9, including the decimal points. And what they've done on this one is they've connected all the cathodes together. So we got two options. I could come down here and put my resistor, put one resistor right there. Now the problem is that when we turn these things on, we have current flow. So if I came over here and put plus 5 volts right there, and then I put 0 volts, 0 volts, 0 volts right here, then this LED would turn on, and this resistor right here would drop around 3 volts. Because this guy's going to conduct so much current. If I come over and put plus 5 volts, and let's say this is 15 milliamps and this is 15 milliamps right here, then what happens now, this guy right here is going to drop 6 volts. Well, we only got a 5 volt supply, so what that means is this LED right here would go off. So what we would have to do is we would have to come in here and we'd have to use a small enough resistor so we could get current flow between these things. But what would happen is that as we turn on LEDs, the LEDs would get dimmer. So the preferred method would be to come over here and put a resistor up here, and to put a resistor for each LED. And then we would come over here, and now we can come over and take the common lead and just connect it to the common circuit. So when I put plus 5 volts, this resistor right here would drop about 3 volts at a certain current. When I put plus 5 volts there, this would drop about 3 volts at a certain current, and all the LEDs would work correctly. So the preferred method is to use one resistor per LED. Now what we do is we call each one of these things is we call them a segment. And then we have this segment. And the segments are given names. This segment right here is called the A segment, and we just come around B, C, D, E, F, and the center segment is called the G segment. Then, most of the time, we will have decimal points. This would be called the left-hand decimal point, and if we have one on this side, this would be called the right-hand decimal point. Usually just RD. So this is why it's called a 7-segment display. And what we can do is we can come over here and turn on segments and display different things. So if I came over here and turned this guy here on, and this guy on, and this guy on, and this guy on, and this guy on, then it would display the number 5 for us. So we can do all the numbers. So 0, I would turn on the A, B, C, D, E, and F, right? A 1, I would probably turn on the B, C. A 2, I would turn it on like this, right? So I'd go across this way. It'd be opposite of 5, a 3, a 4, a 5, a 6, a 7, an 8, and then of course a 9. But what we have to do is I would have to come up here and turn on these different LEDs. So I'd have to come over here, and if I wanted to display a 1, we would have 7 of these inside there. So let's come up here and see what I'd have to do to display this 5. So I've got 7 of them, right? And we won't deal with the decimal point right now. So we're using a resistor in each leg. So to display a 5, and if this is the A segment, so let's go A, B, C, D, E, F, G. Then what I would have to do to turn on the number 5 for a common cathode display is I would have to come over here and put out. So I'd have to turn on the A segment, so I'd put plus 5 volts right there. I'd turn off the B segment, so I'd put 0 volts right there. I'd turn on the C segment, so I'd have to put plus 5 volts right there. I'd turn on the D segment, so I'd have to put plus 5 volts right there. I'd turn off the E segment, right? I'd turn on the F segment, and I would turn on the G segment. And that would cause the right LEDs to come on. Each one of these resistors would drop a certain amount of voltage, whatever is required by the LED at a certain amount of current, and then everything would be hunky-dory. But what I'd have to do if I changed over to a 3, then I would have to come over and do this. Now, what we're using, so we have decoders that will take a binary input and automatically turn on the segments to display the numbers, the binary number that we put on the input. Now we have a 7448. This is a common cathode driver, decoder driver. And then we have a 7447, which is a common anode decoder driver. Now, so that means this guy right here outputs a high to turn on a segment. This guy right here outputs a low to turn on the segment. And so common anode would look like this. One, two, three, 4, 5, 6, 7. And what we have a common anode, all of these are connected together. All the anodes are connected together. So, and we'll come up here, we're going to hook this up to plus 5 volts. And then what we will do is we'll come up here and we'll put a resistor in each leg. I know those are not good resistors. And then we're going to hook this up to the outputs of our 7447. And of course, one output is going to be A, B, C, D, E, F, G. And it'll be, and then we're going to have A, B, C, D inputs, or whatever they call it. So what I'll do is I'll put a binary number in on here, and it will automatically output a load to turn on the correct segments for us. And then we have some other pins on here that we can check. So this is the 7-segment display I'm going to wire up. And you can see the actual 7 segments. Then it's got 2 decimal points, but only one of them's wired up. They have a standard lens on this. So one of the things you buy, when you buy these things, you have to specify where you want common anode or common cathode. And then you specify which decimal points you want. You want them on the left or you don't want them on the right. It all depends on this. 7447 does not control. I think this guy's got a left decimal point. 7447 does not control the decimal point, so you would have to come up with another circuit that actually controls this. So this is the 7-segment display. Now what I'm going to do is pause the lecture now and go ahead and wire this up for it. Wire the first one. So what we're doing is we're over here on page 96, and all we're going to do on this one, you notice we're only using one 330 ohm resistor, and because all we're going to do is go through the segments to see the segments turn on and see basically how it works. I'm pausing the lecture right now. So this is the 7-segment display that we have. It's a common anode, so we can either bring in our power on pin 3 or pin 14. No really need to use both of them. Like I said, what it's done is it's brought a power pin, it's brought a VCC pin out on each side. What we're going to do in this one is we're going to put a resistor here, because all we're going to do is just go in and look at the segments. So here's the A segment. It goes to pin 1. B segment goes to pin 13. C segment goes to pin 10. D segment is pin 8. E segment is 7. F is 2. G is 11. And this is 6. And then left-hand decimal point would be pin 6. And a right-hand decimal point would be pin 8. So what you need to do now is you need to go ahead and do the pin out on 96, figure 13-3. You need to do the pin out on that, okay? So you notice we're missing pin 4 and pin 5. We do have a pin 3. What we're going to do is we're going to use pin 14, even though I could have used pin 3 to power up the anodes. We've got a resistor up here because all we're going to be doing is turning on one segment at a time. What I might do is go ahead and turn on multiple segments, and you'll see how each configuration actually dims out. Okay. So very simple display, very simple circuit. Okay, if that we can really zoom in on this one because we don't have much wiring involved. So here's my resistor. I got it hooked up to my, oops, I don't. I have it hooked up to my plus 5 volt power rail. Okay. Then I have my jumper right here. This is hooked up to common. Okay. And what we're going to do is we're just going to go down through these things and verify the pin out. Okay. So remember, guys, this is A, this is B, C, D, E, F, and G. This would be a left-hand decimal point. This would be a right-hand decimal point. I'm not going to, well, I can technically touch pin 3 because the resistor will drop all the voltage. But I'm going to skip over pin 3 because I know it's power. So here's our pin out. Here's pin 1. Notice the A segment turned on. Oops. Here's pin 1, A segment turns on. So pin 1 belongs to the A segment. Pin 2 belongs to the F segment. Pin 3 we're not going to touch. There is no 4, there is no 5. Here's pin 6. Pin 6 belongs to the left-hand decimal point. Pin 7 belongs to the E segment. Pin 8 belongs to the D segment. Pin 9 is not. Here we go. So this is pin 8. Pin 9 doesn't look like it's connected to anything. Pin 10 is the C segment. Pin 11 is the G segment. Pin 12 isn't connected to anything. And then pin 13 belongs to the B segment. So that's all our segments. This does have a left-hand decimal point. But like I was saying, the left-hand decimal point, the 7447 does not support the decimal point. It will decode the 7 segments, but it will not decode the decimal point. So if I was designing a circuit and I needed to turn on a decimal point, then I would have to do it external, and it wouldn't be that difficult. So here's the A segment. And what we'll do is we'll just, now what I want you to notice is when I hook up the next one, it gets dimmer, right? Sorry I had a little interruption for a phone call, but let's see what's going to happen. So I'm going to come up here and turn on another segment. And as I turn on segments, we should notice that they get dimmer and dimmer. And this is one of the reasons why such segments not used. So now every time I turn on a segment, they keep getting dimmer and dimmer. So if I turned on all 8 of them, then it would get dim so we could see it. So this is the big disadvantage of trying to only use one resistor. Now I've seen some devices that do that because it saves a lot of money. What we're going to use, you'll run into a lot of these. Instead of me coming up here and coming up with 8 resistors, what I'm going to use is something referred to as a resistor pack. So it's an integrated circuit, but instead of being electronic, it's nothing but resistors. And it's pretty easy to figure out because it's 330 ohms, and this uses a technique that's kind of different, where it kind of uses a color code. Let me get down a little closer so we can see this. Hopefully my camera will focus. As soon as it stops bouncing. I don't think the camera's going to focus in on it. There we go. So what it's doing, it's using kind of like a color code, but instead of using a color code, it's using digits. So basically, the resistors, these are through, so like I was doing, I got interrupted again, but this basically works like the color code. 3, 3, so that would be your first number, and the last number tells you the number of zeros to add. So 3, 3, and 1, 0. That means this would be a 330 ohm resistor, and the resistors are in there just crossways. I'm not going to draw up the top, I'll draw down at the bottom. So between this pin right here, so it's a 1, 2, 3, 4, 5, 6, 7, 8, 16 pin dip, so that means we have 8 resistors in there, and the resistors are across that like that. Now these are low wattage, but we're only dissipating around 15 milliamps at 330 ohms. And if we come up here and did the math, so I square, so that'd be 0.015, that's 15 milliamps, squared times 330 ohms, then that would be only 74 milliwatts worth of power. So even a 1/4 watt resistor would work here. That's 250 milliwatts. So about 1/8 of a watt resistor. So this was well within the limits of this little circuit, this little pack right here. So this is what we're going to use when we hook up our 7-segment display. So instead of us coming up here, so we're using this guy right here, and this pin out is correct, okay? So we verified that when we went through our pins, right? So when we come up here and hook up our 7447 in our lab, what we're going to do now is look at the lab sheet, and then we'll come up here and discuss some of these additional pins besides the outputs A, B, C, D, E, F, A, B, C, D, E, F, and G. And of course, the 7447 does not control the decimal. So we just did this, and like I said, we verified the pin out. Okay. Then what we're going to do is we're going to come up here and hook up this. These are our 330 ohm resistors. We need 1, 2, 3, 4, 5, 6, 7. What you're going to have to do is you're going to have to come up here now and draw the outputs of these resistors where they would be on here once you do your pin out. So our pin out for this, and we'll discuss this. So this is the data sheet on the 74LS47 DM. This is the designator that National Semiconductor uses. It says this 74LS accepts BCDs, the 8421 code input data, generates their complementary internal decoders using 7 AND OR. So this is the, let's see if they give us the circuit. Yeah, so here's the actual circuit for a 7447. But we don't really need to know this, guys. So this is very complicated. So you can see how these things become more and more complicated as we go along. All we need to do is understand what this thing does. This is a 7-segment. This is a common anode 7-segment decoder driver. It's got open collector output. So this guy cannot output a high. The only thing it can output is low. Or let's rephrase that. It can only sink. It cannot source. So that means we're going to have a pull-up resistor or something there, and we'll look at that. Why it's a driver is standard TTL can only output about 16 milliamps. This guy can drive, or the one we got can drive 24 milliamps of power. Standard power supply, we already know this, 5 volts plus or minus 5%, which means we could have a power supply between 4.75 and 5.25 volts. This is our pin out. So here's so this one is a little different in that it don't use the ABCD technique to indicate the inputs. So this is the least significant bit of the input, A0, A2, A1, and A3. Now, why they split them up, I don't know. Here's my segment output. So this would be the A segment. This would be the D segment. I'm sorry. This would be the A segment. This would be the B segment, C, D, E, F, and G. And this would be what we call lamp test. So what would happen if this lamp test goes true on pin 3, then we should expect all these outputs right here to go low, no matter what's on the A, no matter what's on the A, on the 1, 2, on the 1, 2, 6, and 7 inputs. Okay. Then we have a technique called ripple blanking. Most of the time, instead of having separate data lines for each digit, what they'll do is they'll have a single data lines that we have that supports all our digits. So what we would do is we would come up here, and it saves a lot of wiring. So what we would do if I was using 2 7-segment displays is, so I'm going to turn them sideways. They just work a lot better that way. Sorry. So 7447, 7447, we would come over here and each one of them would be running their own 7-segment display. And of course it's going to be wired to the 7 thing. And then we got the A3, A2, A1, A0 inputs. And then we have the A0, A1, A2, A3 inputs. And what we would have is we would have 4 data bits coming down here. And then they would hook up like this. And this one right here would hook up to the same data lines. And then what we would do is each one of them would use this ripple blanking input. I think it's low active. So what would happen is it would come over here, and if it put a 0 here, it would put a 1 right there. These would never be energized at the same time. And whatever is on the data bus, this guy would decode it, and it would come up here, and let's say this guy displays a 3. And then they would come over here, and this would go to a 1, this would go to a 0, and then they would, let's say this is 0, 1, 2, 3, and we want this guy displays an 8, so that now all of a sudden this goes to this, and of course this one would display an 8. This one would be blank. So what that means, this guy right here would turn off, and this guy right here would be able to turn on. Now the problem is what they do is they do this at such a fast rate that our eyes blend on. It's like when I'm sitting here looking at these fluorescent lights, I know these lights are turning off 120 times a second. But in my eyes, they look like they're on all the time because my eyes, I forgot what they call it, how fast my eyes can update fast as these lights are right here flicking off and on. Also movies. Movies are done with individual pictures. What I do is what happens is that instead of you seeing the individual pictures, they do it at a rate where your eyes blend everything together. So your eyes kind of keep the previous image when it moves to the next image. You can see this sometimes when you're like taking a video inside your house and you go past your cable box on cable box, and when you look on the video, it looks like they're strobing or it looks like they're flashing, because your camera can capture a lot faster than you can see it. And that's because what they're doing is they're using something called multiplexing. So I could come up here and I could have 4 displays or more. And what we would do is each one of them would use its own ripple blanking input. And what I would do is I would only enable one of them at a time. Whatever's on the data lines at that time would be displayed. And then I move to the next display, next display, next display. And it's doing it at such a rate that my eyes never sees the LEDs actually turn off and turn on. So this is ripple blanking. So let's look at the explanation on the other things. So we know about lamp test. Lamp test is going to turn on make all the outputs go low. RS37 47 decodes the inputs, data, and patterns, indicates a truth table for the segments and illustration. If the inputs are, it says a low signal applied to the ripple blanking input blanks the display and causes a multi-digit. It causes the multi-digit, for example, and we looked at that, right? Of the highest order are connected to the blanking in and out to the RBI of the next one. So the ripple blanking out of this one would be connected to the ripple blanking in of the other one. So anytime this first one is enabled, the next one would be disabled. Sometimes we use that and sometimes we don't. So we have the lamp test. And what this does, it allows us to control 2 displays with 1 ripple blanking input. So when this right here went low, this output right here would go high. When this goes high, this right here would go low, which would enable the next display down the line. As far as I know, this will only work as on 2 displays. The other way, we would have to use this one, and we would tie this guy here high, by the way, if we're not using it. If we're not using lamp test, we would tie it high to a pull-up resistor. So we're not going to use ripple blanking. In fact, I think we are. I think we're going to use this guy right here, because what we're going to do is we're going to connect, I'm going to connect this circuit right here. So what we need to do is we need to do our pin out now. So I'm not going to hook up this circuit right here. We're going to use the actual switches on the trainer. We'll use switch 0, 1, 2, 3, 4, 5, and 6 instead of using, in fact, we'll use these same switches. We'll use 1, 2, 3, 4, 5, 6, and 7 on the trainer. You're going to bring that to A. So here they're calling it A. The data sheet calls this A0. This is going to be pin B, which the data sheet calls A1. This is going to be C, which the data sheet calls as A2. And this is going to be D, which the data sheet calls A3. You'll need to look at the pin outs on the light test, ripple blanking in, and ripple blanking input, and then of course ripple blanking output. And then come down here. We know we need to assign the letters on our pins right here, right? You understand? I think this right here is the A segment, right? This right here is going to go directly to power, either 14 or 3, which one you use. This is going to go directly to plus 5 volts because we're going to use our resistor pack here. And go ahead and make your connections. Or easier, it'll get very confusing. So what you can do is you can number these down here. So give these the same numbers that you do here. And then down here, assign these to a number. Just draw a wire coming out and putting the number over there, if that makes sense. So what I would do, and avoid confusion with getting all these wires crossing down here, the way you have it laid out. So what I'm talking about, probably the best way would be go A, B, C, D, E, F, and G, because that's the way they would actually be laid out on the diagram. I mean, on the schematic. They wouldn't jump around with the output pins like they do on the data sheet. Okay. So what we do, if this right here is A, right? You don't understand? This would be connected to pin 1. So first thing we need to do is number the pins. So if this is going to be B, this would be pin 13. If this is going to be C, this would be pin 10. If this is going to A, B, C, D, if this is going to be D, this would be pin 8. And then if this is going to the E, this will be pin 7. F would be pin 2. And then G would be pin 11. And then down here, let's just duplicate these numbers. So I would come over here and I would connect this. So pin 1, which is A, this would connect to, oops, I made a mistake, guys. Oh, good thing I wasn't recording. So I was recording it, so I made a mistake. I'll try to go back and clip that out. What I was doing is I was doing this guy down there. So the pin out for this, this would be Depending on this one, if this is A, B, C, D, E, F, G. Then this right here, the A segment on the 7442 would be pin 13. The B segment on the 7442 would be pin 12. The C segment would be pin 11. The D segment would be pin 10. The E segment would be pin 9. The F segment is going to be pin 15. And the G segment is going to be pin 14. Then, of course, down here on my 7-segment display, then we would look at the data sheet for the 7-segment display. Erase this. And then what I want you to do is just put the pin number on the 7-segment display up to whichever one is the A segment. So real quick, if I go back and look at the 7447, and this, I'm sorry, the display, which is this guy right here, then the A segment, is pin 1. So what I would do is I would come over here at the bottom of my display, and right here I would come up here and write a 1, which means that connects to this pin instead of drawing it, because it would be a lot easier to do this than to come around and try to draw wires. They would disconnect. So what I want you to do now is to go ahead and each one of these segments, I want you to connect them to the correct pin back here on the 7-segment display.